New Data Center Protocol Stacker AI. Compute nodes in AI and HPC data centers increasingly need to reach out beyond the chip or package for additional resources to process growing workloads. They may command other nodes in a rack scale-up or employ resources in other rack scale-out. The problem is that currently is no open scale-up protocol. So far, this task has been dominated by proprietary protocol. So because much of the highest performance computing is being done in large data centers using custom chips and architectures, and while Ethernet is popular for scale-up, it's suboptimal for AI and high-performance computing workloads. But the two protocols, UA-Link and Ultra Ethernet, aim to address the deficits in current scale-up and scale-out communication. UA-Link is a completely new scale-up protocol, so while Ultra Ethernet builds on the Ethernet 4 scale-up. The multiple communication duties. A computer node is an abstract notion describing some locus of the computing. It has a finite capacity with access to a finite amount of memory and other possible resources such as accelerators by itself. Inadequate for high-intensity workloads and relies on the other nodes over which is distributed over our problem. The protocol that provided a communication necessary to exchange data and coordinate operation can generally be split in three categories. And the lowest level protocol is the die-to-die interconnect, and it's relevant today because of advanced packaging. What looks like a single compute node in a package may be multiple chiplets working together. The protocols that enable this are UCIe and a bunch of wires, POW, as well as some proprietary ones, but all of these communications are invisible outside the package. So, a fully loaded compute node can be thought of a server board with computing, memory, and accelerator attached. There may be more than one processor, however, so system software intermediate which workloads operate on which processors, but that's insufficient for the kind of tasks required for training AIs, so it requires reaching out into the rack or pod to leverage more resources. The goal is to assemble multiple compute nodes while maintaining the feel of a single compute space, multiprocessors and accelerators acting as a large processor or accelerator with unified addresses. This middle communication level is a scale-up. It's where the UA-Link fits into the picture. It works alongside PCIe and CLX, but only UA-Link has the effect of unifying the allocated resources. UA-Link is designed to connect to your main GPU unit for GPU to GPU scaling, said Michael Posner, Vice President of Product Management for High Performance Computing IP Solutions at Synopsys. And it is designed to increase the bandwidth and reduce latency for that connection. So GPUs are just one type of accelerator, and UA-Link will work broadly with any type. UA-Link then abstracts away the division between accelerators. The idea is to interconnect the AI processor to look like one large processor with this pod, said John Ames, Principal Product Manager at Synopsys. Memory access is an important part of the UA-Link's role. UA-Link optimizes the XPU to XPU memory communication across accelerators in a pod, either directly connected to through a fully connected high-radix switch, said Arif Khan, Senior Product Market Group Director for Design IP, Silicon Solutions Group at Cadence, and in a blog post. The looking beyond the rack. Beyond the resources in the rack lie similar resources in other racks, but those racks aren't accessible over the same interconnect holding a single rack together. Ethernet typically communicates from rack to rack, and this is scale out. The top communication level, a resembled scale up, but with the reach is broader than a scale up can provide. So this architecture has one network, for example, PCIe, within the rack and another south side of the rack, or another rack, another level to the network. That is the primary distinct between the scale up and scale out. Ultra Ethernet, address scale out, and SAT POSNER is built on the top of a traditional Ethernet. Counter-grid expansion across the path relies on Ultra Ethernet to accelerate data center Ethernet, essentially a replacement for bulk transfer that rely on a remote to DMA and ROCE today is SAT. Scale down, scale up, and scale out. Figure 1. 4 levels of data center interconnect across the data center, moving from rack to rack, constitute scale-out communication. When the same rack is scaled up, and with the advanced processor package, die-to-die interconnect handle inter-die communication. Source: Bryan-Moyer Semiconductor Engineering. One fundamental difference between the die-to-die and other protocols is the functional nature of the link. Serial versus parallel. UCIe and BOW are both parallel interfaces, typically with forwarded clock, that provide the lowest latency, while requiring many more pins and making skew a much more important issue. UA-Link and Ultra Ethernet employ serial links that drastically reduce the number of accessory signals, but it adds overhead for extracting the clock and reserving the simple values for formats other than reserving the simple values for format other than a non-return to zero NRG. This extra processing is what raises the link latency over what die-to-die protocol provide. The parallel interfaces like a UCIe and BOW that give a very low NOC to NOC latency compared to any interface. Noted Pratyushi Kamal, Director of Central Engineering Solution at Siemens EDA. Scale-up, a greenfield. Today, PCIe and CLX can operate at rack level, but they don't provide the semantic that the creator of UA-Link are designing. Incumbent technology thus consists of a wide range of proprietary solutions. Each company implementing a scale-up must dedicate resources to designing a protocol, and multiple companies doing the same thing as efficiency drain on the industry. We see UA-Link replacing a lot of proprietary interconnects, said Ron Luhman, Strategic Marketing Manager for IP at Synopsys. The designing, creating the proprietary version have used anything from PCIe to Ethernet and everything in between, with the customizations to handle the scale-up, and UA-Link is addressing that. The UA-Link consortium was formally convened last fall with the stated goal of developing interconnect radical specifications that facilitate direct load, store, and atomic operation between AI accelerators. In fact, the UA in UA-Link stands for Ultra Accelerator. It doesn't obviate the PCIe or CLX There's overlap among the duties of those three. However, UA Link is being optimized specifically for AI and HPC workloads. It consists of three primary layers: a transaction layer on top that manages full transactions, a data link layer in the middle that manages each hop, and physical layer 5 that deals with signaling. The first two are new, but the 5 layer leverages what's already in place to speed up implementation adoption. Some extent. Scale-up has been a domain of the PCIe without being optimized for AI. What you will see in PCIe is a lot different design, different chips doing lots of different tasks, where UA-Link is really trying to take an AI accelerator and scale it from 1 to 1000 to handle a single workload, said Lohmann. UA-Link doesn't have all the features and backward compatibility of PCIe, but it addresses specific AI workload needs such as global memory addressing and shared memories. Two initial versions of UA-Link will debut one at 224 gigabps and one can be relaxed half speed minus 200 and 100 versions. Both will feature an Ethernet PHY. After the initial release, minus 128 version is planned that will leverage the PHY from the PCIe Gen 7. The consortium developed UA-Link not to be ideal, but to be realizable quickly because the industry is evolving so fast. The software for AI's industry, AI hardware is moving much more rapidly than hardware can respond, said Lohmann. So getting something out that helps with the scale-up as soon as possible will be beneficial for the whole industry. That means reusing as much possible from existing standards. The idea was that Ethernet and PCIe were the absolute best options out there. Lohmann said the idea was we could get to market fast with a standardized protocol that did basic things required for scale-up architectures. So the consortium took existing technologies. UA-Link 128 is leveraging PCIe like PHY, and UA-Link 200 is leveraging an Ethernet-based PHY. UA-Link isn't expected to challenge PCIe or CLX. We had lots of conversations on positioning of PCIe and CLX and UA-Link, and we firmly believe that they all have their niche within the market, he said. The UA-Link 1.0 specification should available within the next quarter and will be available for free download. Scale-up, building on Ethernet. Ethernet has been widely adopted thanks to its ability to handle a broad range of applications well enough, but some of its policies hurt performance, largely due to the tail latency. Communication latency in Ethernet isn't fixed or predictable. One transaction may complete with no problems, while another may suffer a congested link with dropped packets, necessitating a resend. Even while most transactions must complete in minimal time, these workloads need all nodes to sync up before proceeding, and one link taking longer than the others can hold everything up. It's the latency caused by these awfully few transactions that the term tail latency refers to. They are the tail of latency distribution. When considering latency, it's almost important to realize that latency added by a die-to-die connection is more than just the physical layer delay. The latency, the matter is the NOC to NOC latency, not the phi to phi latency and set comma. This issue is particularly acute for AI and HPC workloads because of the nature of the communication style. Ethernet is most often used to pass the stream of the data east-west or north-south. There's a directionally and a sense of we completed that flow and that's the last we will see of it. But AI HPC workloads relate to the sending out of data for computation and the returning of the result. It's not just the stream that disappears. It's data out and result back, over and over, and more like a respiration than a flow, with each send out of the data being exhaled and the result being in the inhale. Each breathe in or out involves multiple transactions between nodes. Ethernet was developed specifically for being a general-purpose network, said Jay Metz, steering committee chair of the Ultra Ethernet Consortium. It's good if you've got a north and south traffic or east-west traffic. It's not so good if you've got a clustered traffic doing or to or reduce, or any of the other collectives. When you're passing the messages back and forth so they can do their own processing and then send it back, that's more like that breathing environment. Figure 2. Ultra Ethernet position in the data center network. Scale-up happens within the node, make the collection of resource loop like one virtual node. Ultra Ethernet scales those nodes out, and although not illustrated here. CPU can participate as well as GPUs. Source: Ultra Ethernet Consortium. Although the Ultra Ethernet can connect via network interface card, that's not necessary. A fabric endpoint (FEP) could be any device that acts with a fabric address, and that could be suitable Ethernet point on an accelerator itself, said Metz. The magic happens at FEP, which includes congestion, semantic, and packet delivery control. Figure 2 illustrated a simplified data center network with a focus on GPU, but the CPU is also can participate. AI workflows aren't monolithic, said Metz. There are many stages that are boomerang between the CPU and GPUs of different clusters. And even within the cluster, some of the work is best done in CPU, some in GPUs. And the Ultra Ethernet Consortium, UEC, is specifically targeting this type of communication with mandatory features and several options. 1. Given a transaction, only the endpoints have mandatory behaviors. That's intentional so that the Ultra Ethernet network can be built with the standard Ultra switches while not providing the benefit of the Ultra Ethernet. Endpoint installation can proceed without having to wait for new switches. Adding layers to Ethernet. Standard Ethernet specified functionality for layer 2, the data links, and below. It has no knowledge of transactions or endpoints. It's simply moving data hop by hop. Ultra Ethernet builds on this by adding layer 3 network and transport 4. Each transport layers that manage the semantics of a transaction. Must it be secure? Must all packets arrive in order? Must it be reliable? The transport pieces is a big part of what's in Ultra Ethernet, said MS. It gives you mechanisms that can reduce the overall system latency. The sanctity of the layers hasn't been well respected in the traditional Ethernet. Additional features have crept into some layers that might have been moved nearly into others. Ultra Ethernet is trying to avoid that. You want to make sure that when you do something into layer 2, it does layer 2, said Matt. You want to do something in layer 3, it does layer 3. You don't do routing protocols at the MS layer. Layer 3 simply employs the interconnect protocol IP. Unchanged. The networking layer is not currently being addressed by us, he said. That's good in the sense that it helps simplify the process and makes things very easy in traditional data center environment using close or lift spine configuration. Once you start getting into things like Dragonfly, Megafly, and Taurus network topologies, which you will see more often in HPC environment, we are now focusing that we will have addressed that in the future. The transport layer is a mandatory portion of the transport standard implemented in the endpoint. The source endpoint is gonna be called decision maker, and then the receiving endpoint is gonna give the feedback the necessary for those decisions, said Mertz. In the case of the problem packet, instead of sending what would normally be an acknowledge, the destination sends a negative acknowledge, along with some diagnostic information. You'd identify the packet that was either missing or slow and send back to the source, explained Matt. The source marries that to whichever path it had originally chosen and chooses a different path in the submission. Figure 3. The Ultra Ethernet stack includes the transport and the network layers, with the transport layers being mandatory. So far, the network layer employs IP with no changes. The data link and the physical layers add new optional features, estimated in the blue, are required. Those in green aren't changed from Ethernet, and those in a bin are optional. Source Ultra Ethernet Consortium. New features have reduced the tail latency. 4 features that demonstrate the Ultra Ethernet approaches to reducing latency out of the order delivery. And a link level try, flow control, and packet spraying. Many of these transactions are merely sending data from one place to other. As long as it gets there, the order in which it arrives doesn't matter. One can still choose in order delivery, but it's not required. And if some of the data didn't arrive, it's not necessary to resend the entire transaction. Destination endpoint can identify any missing packets with only those being resent. In addition, if along with the path the intermediate node received a better packet, it can immediately ask for the retry the one packet without having to move up the stack and deal with it in the transaction level. Link level retry prevents the protocol further up to the stack from having no determined if something needs to be retransmitted, said MS, pointing to the benefit of the faster response at a lower level, as well as the need to resend the only better package rather than an entire transaction. Because your link level retry is an optional feature, all Ultra Ethernet network won't do it until the switches are upgraded with a new link layer. Another link layer modification related to the flow control. There's a flow control mechanism down at the link level that's credit-based ZMS. Finally, the standard band Ethernet typically picks a path for a flow or transaction and sticks with it for duration of the transaction. If a congested or otherwise compromised path is chosen, that the transaction may take a long time to arrive fully after the necessary tries. Packet spraying an important feature and allows the source of the making separate both decision for each packet and describe it a packaging comparing it to standard Ethernet. If node A talks to node Q, that will go over the path. If node A talks to node X, that might take a different path, he explained. That's the way the multiple pathing works in a regular Ethernet. With packet spraying, you can send the packets over different links, and the network will be handled assembled at the far end. But often this is just data transfer, so it doesn't matter if things are live out of order. Ultimately, three features provide adoption for moving packets faster, and with fewer or limited to tried, it could be the sum of the feature and security could add the latency of physical transaction, but when the system is awaiting the last packet arrival, the tail latency is limited than the nominal latency. Yes, each transaction may arrive a little more slowly, but everyone can get going sooner thanks to the earlier arrival of the last packet. Similar time in the UA link. Ultra Ethernet 1.0 spec is imminent. We are looking at the April or May release. ZMAT is gonna be open for everybody to download. Once released, endpoints can be created quickly, whereas the switching along a route may take longer to upgrade. It ends up being quicker to do ASICs for endpoints than it does do for switches. ZMAT. Generally speaking, switches ASICs are done a single purpose, and the development cycles is considerably longer than the endpoint. They have more function requirements than the endpoint and have to undergo considerable regression testing. Even though the UEC is using standard Ethernet, which IEEE manages, it plans to maintain the Ultra Ethernet control the ongoing basic rather than turning the result over the IEEE to handle. UEC handle standard organization explained that we do have a relation with the IEEE to work with them and share information, but Ultra Ethernet is the UEC protocol. The challenging there is IEEE could say make some changes to each link layer after Ultra Ethernet 1.0 is locked down. Now the IEEE and Ultra Ethernet versions of the link layer are different, so they could remain different. The organization is aware of this challenge and is approaching it by staying in communication with organizations that have a relationship with the Ethernet. We are working with the IEEE, OCP, OIF, SNI, SNIA, the Ethernet Alliance, and the UA Link Consortium, and we are working together to make sure this kind of forking doesn't happen, said Metz. The UA Link Consortium confirmed that they are working similarly. In fact, one aspect of it is already in play, preparing for 400 kbps 5, expected maybe in the 2028-2029 timeframe. That may seem this distance, but the discussions already are underway to coordinate the efforts across any organization that will rely on OFI. Ultimately, the goal is one uniform set of the basic Ethernet features that all the derivatives can build on. Conclusion. It's unclear whether the HPC on its own could justify the kind of effort to going into these new protocols, but AI is everywhere, and it's acting more than a killer app than the HPC. HPC can certainly ride in a coattail, even though the specific of the transaction being that may be different from AI, and even AI will a different style of the transaction at different times. It's for this reason that various options exist, with Ultra Ethernet allowing senders to pick the best semantics that suit a given transaction. Interestingly, both of these efforts are coming due at approximately the same time. Even though there was no coordination between the two organizations, given specs availability in the first half of 2025, there's likely to be a review period during which companies evaluated specs before adopting. The working them into silicon will then take a list another way. So these protocols are likely to start showing up in data centers in the late 2026. Okay, today I read this article. New data center protocols tackle AI. Thank you for your time. See you next time.